Space. It's often imagined as a place of serenity, a silent canvas dotted with stars. But that silence is deceiving. Beyond the atmosphere, beyond the protective shield of Earth's magnetic field, lies a hostile environment shaped by physics, extremes, and indifference. There's no weather, no sound, no breathable air. And yet, every satellite, probe, and telescope we send there must operate flawlessly for years, sometimes decades. To do that, they must survive conditions far more violent than they appear. No crashing waves, no storms, but instead, relentless radiation, micrometeoroids, and temperatures that swing from blistering heat to absolute cold in minutes. So how do we protect these machines, these instruments of science and discovery, in an environment that cares nothing for survival? The answer lies not in armor plating or thick shields, but in something surprisingly delicate, something that looks, at first glance, like household foil. On Earth, we take heat transfer for granted. Our atmosphere evens things out. Heat moves by conduction, convection, and radiation. But in space, only radiation remains. There's no air to carry heat away, no breeze to cool a sunlit panel, no shadow to insulate against rising temperatures. This creates extreme thermal challenges. A spacecraft basking in direct sunlight can reach over 250 degrees Celsius. Just around the corner, in shadow, it may plunge to minus 160 degrees Celsius. These swings aren't occasional. They happen every orbit, every 45 to 90 minutes. Electronics expand and contract, connections loosen, batteries degrade. Without control, spacecraft can freeze, overheat, or slowly tear themselves apart. This thermal chaos demanded a solution that was both elegant and reliable. Engineers couldn't simply slap on thick walls or plug in a heater. Weight is the enemy of launch, and every gram counts. So instead, they turned to a material that reflects, that buffers, that protects, all while weighing less than a paper envelope. That material is called multi-layer insulation, or MLI. Though it's often mistaken for aluminum foil, MLI is a far more sophisticated invention, a finely engineered shield made of science, not kitchen supplies. MLI typically consists of between 10 to 100 layers of thin plastic film, like Mylar or Kapton. Each layer is vapor-coated with a trace amount of metal, usually aluminum, though gold is used in certain missions where ultraviolet protection is needed. These sheets are incredibly light, mere microns thick, but when stacked with small gaps in between, they form a powerful thermal defense system. The layers are separated by tiny spacers, mesh or polyester netting, to prevent contact. Because if two reflective layers touch, heat can transfer through conduction. The brilliance of MLI is in how it disrupts that. By reflecting radiant heat layer by layer, MLI dramatically reduces the amount of thermal energy that reaches the spacecraft's sensitive core. Imagine it as a thermal mirror maze. Each ray of heat reflects and scatters, never quite reaching its target. Now look again at the surface of a spacecraft. You might notice that it appears crinkled, messy even, a far cry from the smooth panels we associate with precision engineering. But this texture is intentional. Those wrinkles are not a sign of damage or neglect. They are a feature, not a flaw. Wrinkles increase the effective surface area and decrease heat conduction. A smooth, taut surface would allow heat to flow more easily through contact points. But a wrinkled one, it disrupts that path. It reflects more. It traps microair pockets. It keeps each layer of insulation doing its job with greater efficiency. MLI is applied by hand in most cases, shaped and stitched like a finely tailored garment. Engineers wrap it around each mission's unique geometry, over antennas, around propulsion tanks, along awkward angles. The process is delicate and time-consuming. Every cut and fold must be precise, because once launched, there's no going back to adjust it. Thermal control may be the most visible role of MLI, but it's far from the only one. In the vacuum of space, dangers come in many forms, and MLI has evolved to address more than heat alone. Micrometeoroids, some no larger than a grain of sand, travel at speeds that can exceed 50,000 kilometers per hour. At those velocities, even tiny particles can punch holes through metal. While MLI won't stop a major impact, its layers can absorb and disperse the energy of smaller collisions, adding one more layer of protection in an already dangerous domain. MLI also reduces outgassing, the slow release of gases trapped in materials, which can fog lenses or interfere with scientific instruments. And it helps shield electronics from solar and cosmic radiation by reducing electromagnetic interference, allowing delicate onboard systems to function in a chaotic radiation environment. This makes MLI not just a thermal blanket, but a true multi-role protector, one that guards against heat, cold, radiation, vibration, and collision. If you've ever seen photos of the Apollo lunar module, the ungainly, insect-like craft that landed on the moon, you've seen MLI. Its legs and base were covered in gold and silver layers that shimmered against the gray lunar dust. That was some of the earliest use of this now critical material. Since then, nearly every major spacecraft has carried MLI. The Hubble Space Telescope, wrapped in it. The Voyager probes, still sending signals from interstellar space, protected by it. The James Webb Space Telescope, our most advanced eye on the universe, doesn't just wear it, it depends on it. Webb's giant sun shield is essentially a 5-layer MLI system stretched across a structure the size of a tennis court, keeping its instruments cold enough to detect faint infrared light from the birth of galaxies. Each mission has refined the design. Each application has brought new innovation. And through each iteration, the foil that started as an odd-looking layer became an icon of spaceflight. But MLI didn't stay in space. You've probably seen it, maybe even used it, though you might not have realized what it was. Those shiny foil blankets handed out after marathons? That's based on MLI. Emergency rescue wraps? Same concept. They reflect body heat back toward the person, just as spacecraft reflect solar heat away from vital components. The same science that protects a billion-dollar satellite from solar radiation now keeps hikers alive in the cold and first responders safe in the field. From orbit to Earth, MLI has become one of space exploration's most quietly influential legacies. So why are spacecraft covered in foil? Because in space, survival is not guaranteed. Because conditions shift in seconds. Because every instrument, every byte of data, every distant photo depends on hardware staying functional in a place that was never meant for machines. MLI may not be flashy. It doesn't glow. It doesn't move. It doesn't thrill. But it works. And in the cold calculus of engineering, that is the highest praise. It reflects not just sunlight, but decades of human ingenuity. It carries the quiet confidence of a solution that has stood the test of time and space. It is proof that sometimes the most essential part of an extraordinary machine is the part most people overlook. So the next time you see a spacecraft wrapped in shimmering layers, remember, that's not tinfoil. That's survival, folded and stitched by hand. That's science, wrapped in light. That's how we fly.